When a pod fails DNS resolution, the first action is inspecting its etc resolv.conf. Verify the name server entry points to the cluster IP of the kube-DNS or CoreDNS service, typically 10.96.0.10 in default installations. If this IP is missing or incorrect, the pod definition or CNI injection failed. Next, confirm the search path includes the service account namespace and the cluster domain suffix, usually svc.cluster.local. If the pod is using host network true, it bypasses the cluster DNS, inheriting the node's configuration, which is a common misstep for application pods. Immediately check the pod status using kube-control describe pod name, looking for CNI errors or initialization failures that precede DNS issues. The next vector is the CoreDNS deployment itself. Execute kube-control get pods n-kube system, label k8s app.kubedns. All CoreDNS pods must be running and ready. If they are restarting, examine the logs immediately using kube-control logs n-kube system CoreDNS pod. Look for errors related to configuration parsing or binding to port 53. A frequent issue is resource starvation. Check the pod resource limits and requests. If the pods are healthy, verify the associated service endpoint status. The service must correctly map to the running pod IPs. If endpoints are 0, the service selector is incorrect or the pods are genuinely unhealthy despite reporting ready. CoreDNS behavior is defined by the CoreDNS ConfigMap in the kube system namespace. Retrieve the Corefile configuration. Pay close attention to the forward plugin definition, which handles external lookups. If external resolution fails, ensure the upstream name servers listed in the forward block are reachable and responsive from the CoreDNS pods. Misconfigured zones or incorrect loop detection settings can cause internal resolution failures. For example, if the cluster domain is incorrectly specified, internal service lookups will fail silently or time out. Always validate that the Kubernetes plugin is correctly configured to handle cluster domain lookups. Network policies frequently intercept DNS traffic, leading to timeouts. If a pod cannot resolve, check if an active network policy restricts egress traffic on UDP port 53 to the CoreDNS service cluster IP. Policies are often overly restrictive, blocking all egress unless explicitly permitted. If you suspect a policy, temporarily apply a permissive policy to the failing namespace or pod to isolate the issue. Remember that DNS uses both UDP and TCP port 53, although UDP is primary. Ensure your policy allows both protocols for robustness, especially for zone transfers or large responses. Use kube-control get network policies AA to list all active rules and analyze their effect on the failing pod's namespace.
DNS resolution relies on kube-proxy correctly programming IP tables or IP virtual server rules to route the cluster IP request to the CoreDNS pods. On the node hosting the failing pod, inspect the IP tables rules, specifically the kube services chain. Verify that the rule corresponding to the kube-DNS service cluster IP correctly directs traffic to the backend pod endpoints. If the CNI plugin itself is unhealthy, pod networking initialization fails entirely, preventing any communication, including DNS. Check the CNI daemon set logs for errors related to interface creation or IP assignment on the node. The node's /etc/resolv.conf is critical because the kubelet uses it to determine the upstream servers for the cluster DNS configuration. If the node's configuration points to an unreachable external server, CoreDNS may fail its external lookups. However, pods generally use the cluster IP, not the node's configuration directly, unless host network is enabled. If you are debugging external failures, test resolution directly from the node using dig to confirm the node's connectivity to the configured upstream DNS servers. This isolates whether the failure is internal to the cluster or external connectivity related. When external domain resolution fails, the issue often lies in the path between the CoreDNS pod and its configured upstream servers. Use tcpdump on the node hosting the CoreDNS pod, filtering on UDP port 53 traffic destined for the upstream server IPs. This confirms if the query leaves the node and if a response returns. Firewall rules on the node or external network security groups might be silently dropping the egress traffic from the CoreDNS pods. High latency to the upstream servers can also cause timeouts, even if the servers are technically reachable. Consider implementing the health and forward plugins with specific timeout settings in the Corefile to mitigate slow responses. To definitively test resolution from the client perspective, deploy a dedicated debug pod using an image like Nikolaka/netshoot. Inside this pod, use dig @cluster IP/service name to force queries directly to the CoreDNS service IP. This bypasses potential CNI routing issues and confirms if CoreDNS is responding correctly. If dig works but application pods fail, the issue is likely specific to the application pod's configuration or network policy. Use NSLOOKUP to test both A records and service records, ensuring that service discovery, specifically SRV records, is functioning correctly for headless services. Common remediation steps include increasing CoreDNS resource limits if CPU throttling is observed, or adjusting network policies to explicitly permit UDP53 egress. If the issue was a misconfigured core file, ensure the ConfigMap changes are applied and the CoreDNS pods have successfully reloaded the configuration. Implement Prometheus metric scraping for CoreDNS to monitor query latency and error rates proactively. Persistent DNS failures often stem from inadequate resource allocation or conflicting network policies that were not fully tested during deployment. Always verify that the cluster domain suffix is consistently applied across all namespaces.